All right, hello, we're back. The lighting is amazing because it snowed. All right, so today we're continuing on the Secereum Boot-camp journey, and specifically I've gone through Security Pitfalls and Best Practices 101 and 201, and I'm starting to think that some of these Substack articles could be like, Security Pitfalls and Best Practices 50 instead of 101 and 201. With that being said, reading it from front to back is, at least in my head, good to at least see the terminology and see how people discuss certain items. I'm sure that there's an 80-20 rule for all this stuff within really everything, but specifically within this specific smart contract auditing is of the 200 points that are made here, 201 points that are made here, probably 20% of those are the ones that truly matter, and they have 80% of the impact, which is kind of the old 80-20 rule. I've highlighted a few items per usual, things that jumped out to me that I wanted to share with you and that we can check off together. I've pulled these from both 101 and 201. And like I said, there's tons of these, so I'm missing a ridiculous amount of information. But I just wanted to call out a few items that I found interesting and a few resources that I found interesting by reading through a lot of this stuff. And one thing I will say is that 101 is really well done in the sense that there's a lot of links that link out to additional resources that cover the either security pitfall or best practice that's mentioned inside of this blog. So kudos to the individuals that put so much work into actually curating all this information from all the other locations. So bingo bongo. All right, first things first is the two kind of big takeaways I took from this is, first off, this was a huge breath of fresh air in comparison to specifically the ones on Solidity, because like I said, that was basically a copy and paste from the documentation, so that was very dry reading. This was more interesting and more up my alley of interest, specifically talking about how you can exploit certain aspects of smart contracts, etc. And the other thing was that this gave me a lot of interesting ideas, a lot of things that I want to do going forward, future pieces of content for things like this where I can actually go through Sliver because they have a specific repo I'll share with you that breaks down a series of known vulnerabilities. And I'm going to use Slither. So I have a few ideas of how I want to do this, but there's some good content around this. And there's also some good content around actually pulling out the official source code for vulnerable smart contracts that were hacked historically, and then doing basically a walkthrough on that attack and specifically calling out the bits of code that caused that attack to occur and the millions of dollars to be lost for those specific historical attacks. So those are two things I'm excited about, and I will mark that off because that's what we do here. In addition to that, I will show you the Slither repo quickly. So it's not mentioned in Slither, but I know there's a ton of them in here, so we'll just hover over these until we find one. There we go, that wasn't hard. So you can see that basically there's a lot of these links that are linked from that article that come into the Slither repo. And inside of the Slither repo, and this is a tool that I'll use eventually, it's a static analyzer. And specifically in here, there's a repo in here with, I think it might be in here. I'm not sure where all of it sits, but it basically comes out of the tool. So when you run the tool over top of your code, it then pops up these answers and it links you back to this wiki. But the really cool thing about the wiki is it kind of walks you through and explains specific exploits. So you can see that it's referring to variables that should not be constant. It basically tells you the severity, all that stuff, and then it shows you an example. And this is a really, really great resource to really understand known vulnerabilities that are easily mitigated if they're known like this. That was one interesting bit that I pulled from here. The next thing is versioning. So this is something we've discussed previously in other videos, but I wanted to call out a few items that I found inside of this article that I found insightful. The first thing here is somewhat of a surprise, but it shouldn't have been, is that when you're running through your version of Solidity, they mention that it's best to actually not use the newest and not the oldest. You want to find that happy medium. So it's kind of like the old wise tale or the old fairy tale where like the bears and they had the soup or something like that. Don't know what it's called. But porridge, it's porridge, the porridge. And here you can see I've stated that new but not too new. The point they mention in here is that there's a line that needs to be walked between using a version of Solidity that's hardened based off of historical attacks and lessons learned, but also not doing something that's too cutting edge because that opens you up to new vulnerabilities that are unknown. And one thing they actually mention here around doing this is the compiler that you use specifically, you should use the most up-to-date compiler to ensure that you are checking for new vulnerabilities that have not been covered in the old compilers. But when you deploy, and not test, when you're deploying, you should then lock the compiler and lock that version to a specific set. So instead of using the floating versions that we've discussed previously where we have the caret or a variety of other symbols, this caret's basically stating that we want to use anything 8 and up within the second integer over. So we want to basically use version 8 and 9 and probably stay in the major. So 8.1, 8.2, 8.3, etc. And that's really interesting there. And the mention here that I've linked out to, let me try to find the source. And I'll link all this stuff in the description as per usual. Probably what's easier if I just do this. You can see here it basically states this is the resource I wanted to share. So if we go to the top here, there's a GitHub repo from this place. And this repo basically walks you through how to build secure smart contracts. I read through some of this. I think the thing that was most useful for me was the high-level best practices. So under high-level best practices, they basically walk you through, it's basically an article talking through some of the common patterns and practices that you should use when creating a smart contract. And specifically in here, they talk about versioning. So if we do version here, you can see they discuss a lot of what I've already shared. So that is a good resource, and you should definitely check it out. And we're going to mark that off because we finished it. Oh yeah. Next, patterns. Oh, this one's good. Okay, function patterns. So specifically within a function, there's a pattern that one should follow to ensure that you're avoiding reentry. I think it's called reentrancy attacks. I kind of have a general intuitive understanding of what it is, but I'll probably make an entire video or blog post on that topic specifically because it is specific to blockchain-oriented things. And this pattern here for functions is, you can see it's basically you check, affect, and interact. The way it's explained here, and I have a code snippet I'll show you, is first things first, within the function you're going to run a check. And that check's going to basically say, who called the function? Are the arguments in range? Do they send enough ether? Did they send enough ether? And does this person have tokens? And there's more as well. But really the premise here is that you want to do some sort of check in the beginning to ensure that the function is executing on what it should be executing based off of previous interactions it's had. So that's the first thing is you check. Next thing is you affect. So after you've checked, now it's actually make an effect on the state within that function. So the state variables inside of it and the other state items that you're tinkering with. So now you can make your effect. And then after you've done that, the last thing is actually interact with other contracts. So sometimes people actually swap these and they'll actually do an interact and effect or something vice versa. And that leads to potential exploits for reentrancy attacks and alternatives as well. And I think if I go to my code snippets here, here you can see down here, so I have this example. I pulled this from, there's a blog article that I'll link as well that actually has really insightful information that's useful. Is this one here where it talks about best practices for smart contracts. So this was from Consensus. They have a highfalutin smart contract auditing firm, and in here they basically walk you through some of the common pitfalls and practices. And I think, maybe it's not here. Let's try to find it. Okay, it's not there. Sorry, I jumped ahead. So inside of the Solidity language documentation, there's actually an article in here that I've not read the entire thing. I will, but it's security considerations for programming within Solidity. And specifically, they talk to the point that I've made is this section here where it talks about the pattern and how to utilize it. And in this example, you can see there's a code snippet here. And if we look at this, we can see we have a contract and two functions and a mapping. So here it's a breakdown, right? So here we have our mapping. We have our function that's doing a check. And inside of here, this function actually has the entire pattern because not all functions will have the entire pattern based off of what they're doing. But you can see that the first things first with the functions, we're doing a check. So we're ensuring that the value is then assigned to the sender and we're checking the balance there. Next thing is we have another check here with the withdrawal. So we're going to check to ensure that the sender has an amount more than 0. Then we want to ensure, then we can make an effect, so we can then reduce the amount from the sender. So that's our effect piece. And then we have our interact piece. Or okay, so now we're actually going to call transfer, which is being called from another contract. So we're going to say the sender, we want to transfer this amount. And this is kind of the breakdown, and this is the consideration that one should have when creating their functions and when auditing smart contracts. You should look for this kind of thing, because if they've switched things around, then that opens them up for an exploit, such as re-entry that I mentioned. And that is that example. So we'll actually remove it so I don't have to look at it. All right. Dunzo. Next thing. This one's interesting. So I came across this while watching a video series, and I remembered it when reading this article. So we'll actually go to my history, and you can see, actually, let me go back. This guy here, he created a 16-hour video. Let's try to find it. Maybe a free code. Okay, here we go. So this video is really long. I've not completed it. You can see I'm about 11 hours in. And specifically in this, he talks a lot about Chainlink, and specifically how Chainlink creates randomness and brings it into the blockchain, because there are a few methods of actually creating true randomness. And this is a problem and a security flaw with really not just blockchain, but outside of Web 2, in Web 2 and also in Web 3, is to create something truly random is a very difficult task. And what Chainlink does is they actually go external, and I'm pretty sure they utilize C-Spring or something along those lines. And C-Spring is just a method of utilizing your OS and a series of human interactions in the environment to create somewhat true randomness. And you can see that there's a simplistic breakdown here showing that you have your source of entropy. I don't know, I think they spelled that wrong in this. I pulled it from Google, not me. And here you can see that basically your mouse movements, your keyboard strokes, audio signals, and a series of other things that have true entropy inside of them are the source of randomness. And that puts it into a pool, which if you have Linux, it's sitting inside of those folders. And then C-Spring does the generation of a random number for you. So that's that's off-chain, right? So getting that randomness is then pulled through an oracle like Chainlink to bring that randomness in. There was also another mention here, I think it was inside of the Substack that I was reading, where there are alternatives of actually creating randomness on-chain. And it's not 1,000% sure like how this works, because I didn't really take the time to read it. But there are methods of doing this, and you can do it on-chain. And it's explained here under Randao. And that was the interesting bit there. So randomness, it's hard, both in Web 2 and Web 3. All right, so this isn't necessarily, I guess it's a denial of service attack if it's associated to cost and things like that. Here we have a talk around loops, and specifically loops with state variables inside of them. That can be very, very costly, and it should be avoided at all costs if need be. And reason being is that as you loop over a piece of code, and I have a code snippet to share, I'll show you in a second. As you loop over that loop, you're consistently updating that state variable. And as you do it, it's calling a specific opcode, which is like an assembly in Ethereum. And this specific opcode is very expensive, because you're updating that state variable, which then sits on the blockchain. So you're consistently updating the blockchain, and that has associated gas costs to it, which we've learned in previous videos. And that's something you want to avoid, specifically with putting state variables inside of for loops or while loops or whatever loops. All right, if we come here, we can see this code snippet that kind of shows it. And let's see, okay, so this function here is labeled bad. So this is no good, shouldn't do that, and this is good. And that's kind of the discernment. So we have our state variables out here. So we have loop count and state variable. And below that we have a function. And inside of this function we have a for loop. That for loop is then iterating over the state variable and incrementing it from within this for loop, which is no bueno. Here we have a different kind of a slightly different setup. So we have a local variable that is then storing our state variable here. We're going to run our for loop. We're going to increment our local variable, and then after we've incremented our local variable to the point where we're finished and we've hit the loop count of 100, now then we're going to take that local variable and then update the state variable. So instead of updating the state variable 100 times within our for loop, we're only going to update it once. So that's going to save us 100x cost by just adding that small snippet of code. So pretty simple, but really important if you want to save yourself some money and also your users money. All right, next is functions. And this was interesting. I have another code snippet for this as well. With both functions and state variables, I'm pretty sure if you've added no visibility modifier at the end of it, then the default is for it to be public. So here you can see I've stated that default open, not default close. And this applies to functions, but I think it's state variables as well. And that in itself is no bueno, in the sense that if it's default public, that means that there's a potential for both humans and contracts to interact with this function unexpectedly, causing either errors or potentially exploits. So if we go in here, I have another example here. So we have our func visio, and we have a few things here. So we have a function here for buy, state variable x, another state variable. This is labeled as private. Okay, so really if we look at this and this, these are kind of the difference. So this section here is a good section, so this makes us happy. This section here makes us sad. Reason being is that this integer here, the state variable, has no mention of the visibility. So it's publicly default public. Same thing applies for this function. There's no mention of the visibility here. So that means that this is going to default to public. Same thing applies here. So here we have our uint, and this is mentioned to be private, so that's good. And then here we have a function. This is mentioned as external, which is fine, public and internal. So all of these have been explicitly stated instead of allowing the default to be public. And that's another important piece here, is when writing those functions and writing those state variables, always try to explicitly state what the visibility is, ensuring that there's no spooky action at a distance. All right, that is done there. And I think this might be the last one, the second to last. This is a bit shorter. All right, separation of privileges. So this is a common thing in Web 2, where you have a series of roles and capabilities for those roles and things like that. This is similar to like identity access management within AWS, where you have a series of really critical roles like admin, things like that. And you want to ensure that this admin, to take actions, there should be a series of checkpoints in between them and that critical action they're taking, to ensure that this is not an incorrect or disagreed upon action by others. Yeah. Within Web3, the same concept applies, but it's within multi-sig wallets. And here you have an interesting image basically that shows this. It's very simplistic, but it kind of gets the idea across. Where we have different users here, and all these users have keys, and all those private keys have to be signed, and those signatures have to be validated inside of this multi-sig wallet here. So if you have, and it's majority rules, so it's either majority rules or a set number has to be met. So I think it's like 4 out of 7 or 5 out of 7, and then there's like 7 out of 9, and then here you can see it's 2 out of 3. You can have as much as you want, really. And here we have 2 out of 3. So since those have checked, that means this multi-signature is unlocked, and then there's a specific action or transaction that occurs there. You'll see this commonly within, I think, DAOs, where you have a series of voters that are voting on certain decisions that should be made, and also funds delegated. And basically by doing that, you're agreeing upon the group, and you're getting majority rules or whatever number that needs to be set for that thing to occur. And here, actually, real quick, you can see some actions that are mentioned inside of the blog post that I read for Secereum. That some of the major actions or critical roles that occur, such as pause, unpause, and shut down a contract, emergency fund drain, upgrading a contract, allow and deny lists for certain addresses and things like that. Those are some of the small examples that you would want to put a multi-sig potentially in place to ensure there are checks between that role and that action. All right, and then last is events. So we talked about events in the past. Specifically, I wanted to mention here that I found somewhat interesting and I didn't know is with events, when you're logging events, there's a certain subset of events that are kind of, I don't think it's like officially agreed upon, but it's unofficially agreed upon amongst the community, and it might be official in some sense, where there's a subset of events that need to be indexed. So there's two different types of events that are aggregated off-chain. There's indexed events, and then I think there's like graph events or something, what it's called, raw events. And the indexed events are easier to access based off of how they're set up within this thing called, I think it's like a bloom filter. And within that bloom filter, it allows us to search those specific events faster due to the way that they've been indexed off-chain. And some of the common events that should have this effect are such as ERC20 transfers and approval events. There's a series of others, but those are some of the two that were mentioned in this blog post. And then in addition to that, another really interesting thing about events and emitting events is specifically transactions. Remember, there's two things, right? There's transactions and there's messages. So transactions tend to be humans and messages tend to be robots, aka contracts, ROBs. And with that being stated, that's not always common. So humans can do messages as well. They can incorporate that into the transaction. But the point I want to make here is that when messages occur between contracts or between functions internally inside of a contract, they're not default logged. So they're not default emitted, and those events aren't logged off-chain. So if something happens and you've not emitted that, if you've not set up an emission for the event to occur, then there's a good chance that you're not going to see that because it wasn't logged and you can't see it off-chain. And that comes in handy when you're trying to do incident response or doing analytics off-chain for an app or just trying to interact with anything as a dApp. And that's really the point made here, that when you want to explicitly log an event for a message that's occurring between two contracts or between a externally owned account or a contract or vice versa, it's important that you actually include the emit item mentioned there. So it should be emit this item, and then that event should be logged. And I think I have an example. I don't have it ready, but we will wing it. All right, so here you can see inside of this this blog that I mentioned that was pretty great, and you should read it, is they talk through some of this information here. And if we scroll down a bit, you can see an example here of that emit mention that I stated. So here inside of this contract, we have a few different items. So we have a contract for charity, and there's an event here that's explicitly stated. So we're defining the event that we want to keep track of. And specifically, you can see that there's a donate function, and down here there's another contract, which is then calling this donate function from the other contract. And when it calls this function specifically, traditionally, if there is no emission that's mentioned, so you can see here that when this function is called donate, we're going to emit an event that is then logged off chain. So we're calling it here, we're emitting that event. But without that being there, if we go up here, this is the bad version. There is no emission, there is no log, so you can see there's no specific event mentioned, there's no emission here, and when this is called down here, it's not going to be logged. So off-chain, you're not going to actually see that this internal transaction of donation occurred between this contract and this contract. And that's something that one should keep in mind when developing smart contracts, is mainly due to the fact that if this is the case, then there's a lot of things happening behind the scene that could either be malicious or just a straight up accident. And with that being said, I think that is everything. So internet, I hope this is useful. It's a lot shorter, but hopefully it's a good thing. And I'll see you in the next video.